In this video I'm going to show you how you can use PF depth for 2D to 3D stereoscopic conversion using semi-automatic conversion techniques. And I'm going to take you through a shot from beginning right through to the stereo render. So here we are in PF depth, and this is the shot that we're going to work on, so I'm going to select that and open it up. And some of you may have seen this shot on the website already, but I'm going to take you through all of the steps to do a semi-automatic stereoscopic conversion on this. As I mentioned once before, it would typically be a difficult shot to work on, basically because of all of the occlusion that's happening in here. We've got all of these, rocks, we've got grass, we've got twigs overlapping things, all kinds of stuff going on in here. So to try and rotoscope this would take forever. So what we want to do is try and automate as much of the process as possible and get results as fast as we can, and therefore we can be more productive. So the first thing you typically want to do is set the film back for this, and this was shot with the Canon 7D, which I know has a horizontal film back of 22.3. And when I enter that, it's giving an automatic vertical measure of 12.54 millimeters at 1:1, and that's because on many digital sensors, only a portion of the sensor is actually being exposed depending on what resolution you're capturing in. So if I set the horizontal, it's automatically going to set the vertical. I could then say this is a preset. If I want to, I'm going to call this Canon 7D3, just because I've made a couple of presets already, and then it's already available to us in our list. The next thing we might want to do is set the focal length if we know it, but we don't. So what we're going to do is set the near plane and the far plane. So that's going to establish our world space. So I might say that the near plane is, let's say, 5 feet away from the camera. And the far plane is, let's say it's, let's say 25 feet away from the camera. And if I take a look at this now in perspective, you can see the world space that's been established. We've got our initial camera position here, but if I make any changes to this, you can see how this affects the camera frustum. If I change this to 1 foot, the field of view is right butt up against the front of the camera. So let's change that back to 5 feet. And of course I can turn the frustum on and off if I want to. I can show the ground plane and I can show the horizon if I wish. So we're just going to leave those things turned off for the time being. So the next thing we're going to do is actually track this camera, and for this we're going to use PF Depth's own built-in point tracker, which is the Simple Track and Solve node. So this is using the same algorithms that our match moving products PF Track and PF Match It will use, except you're able to do match moving right here within PF Depth. What you're looking at here initially is a very simplified interface, and it's literally a 2-button solution. You track it and you solve it. But if you've got a little bit more experience with camera tracking, you could choose to go into the advanced settings, and this is where we could actually input a known focal length if it was known, if it was a constant or variable focal length, if it was a free motion or a nodal pan. We can also define how the shot gets tracked using the tracking parameters, so how many features are going to be placed per frame, what is the separation in pixels, all that kind of stuff. I'm just going to use the standard defaults, so we'll go back to the basic view and we'll click track, and you can see that the features are now being tracked into the sequence. It's going to track it once to establish all of its features, and then it's going to track it again in reverse to extend the duration of the features that it's already placed. So for the sake of time here, I'm just going to speed this up, and we'll pick it up once it's finished its track. Okay, so now we're finished, and what we can do now is actually switch over to the Solve button, and this is going to take all of our tracks and create our camera solution. Okay, so now we can switch over to the advanced settings, and this is where we can take a look at the error counts. First of all, let's take a look at this in perspective and see what we've got. And the track's actually not too bad. There's nothing sort of floating out here in space anywhere, so we know it did a reasonably good job. But we've got some pretty high intensity errors here, so what we can do is use the trim function to ignore everything that's over, let's say, 1 pixel of error per frame, and then I can select improve the solution, and all of that data is still there. We can always reintroduce it, but any of those high intensity errors are actually no longer contributing to the solution, and only things that are kind of over 1 pixel, under 1 pixel of error per frame are actually going to contribute. So that might give us a little bit more of a solid result. Now, if we wanted to, we could always, this isn't necessarily, applicable to 2D to 3D conversion, but if we wanted to, I can use an orient scene node to orient the ground plane. So the way that I'll do this is use the marquee tool to select a point. So I'm just going to darken the screen up so you can see things better. I'm going to select that as my origin, so I'll set that as my origin. And then I can orient my scene. I'm just going to basically rotate things around here. So they make a little bit more sense. So I'm just going to tilt that up, rotate it around. Let's say about like that. So now we can play that back. And the ground planes, well, you know, for match moving, if I wanted to have a character step on this, it might not be perfect, but it's certainly a lot closer than it was. And for this, as I say, for the sake of stereoscopic conversion, it's probably not even necessary, so we just do it for the sake of consistency. So the next thing that we're going to do is, now that we've got our camera track, our camera position, and all of these points that we've solved are all going to act as depth cues for where individual pixels live relative to the camera's position on any individual frame. And that's because we're creating a per frame per pixel depth map. The way that we're going to do that is we are going to use the ZDepth solver node, and this is going to allow us to automatically synthesize a depth map based on the depth information that we established because of our camera track. You can see our camera's position. And what we're going to do is solve a single frame depth map. So I'm just going to use all of the default parameters and click solve, and it's going to synthesize a depth map for this first frame. And there it is. Now we're seeing an overlay of the depth map over top of the plate. And if we take a look at this in perspective, we can see the depth map that it's created. I can increase the depth cut to 100%, and that's going to fill in all of those gaps. And let's drop the transparency so that we're actually only looking at the depth map. And then we can also adjust the gamma so we can see a little bit more of the detail in there. Now this isn't affecting the image, it's literally just for display purposes, but this is going to allow us to visualize if there's any strong errors that we're going to need to sort out later. So that's our first frame depth map. So now what we're going to do is I'm going to add in a ZDepth tracker node, and this is going to take this single frame depth map and track it into the rest of the sequence. What I'm going to do is increase the position weight up to about 90, because the position weight is basing a lot of its solving on camera movement as opposed to object movement. If there was more object movement, I might choose to increase the spatial weight. But we're starting on frame 35, so what I'm going to do is take that initial frame and start tracking it in to the rest of the sequence in reverse. Now what's cool about this is that it's not just taking what was present in the field of view and tracking it in. As additional pixel information enters the field of view, it's taking that into account and contributing to the pre-established known depth information that it solved on its first frame. So it's continuing to kind of reanalyze itself, but it's giving you a faster result than it would be if we were calculating a depth map on every single frame. Now, after we're done with all of our work here, and I'm just going to bring that back to frame 34 and start tracking it forward. Once we're done with this method, where we're taking a single frame depth map and tracking it in, I'm going to show you the difference between doing it this way and calculating a new depth map for every single frame, which is, you know, certainly a lot more time consuming, but it can solve a lot more details. So it's kind of a trade-off, you know, how much time do you have to get through a shot versus, you know, how much detail or how accurate do you want the result to actually be. So we're almost through this shot, so once it's done, we'll go on to the next step here. Okay, so there is our tracked in information, but as I scroll through here, you can see there's quite a bit of chatter going on in all of these individual gray values. And if we take a look at this in perspective, you can see how it's actually reacting with the image. There's a lot of inconsistency frame to frame. So what we can do in PFDepth is use the ZDepth merge node to compare depth map information across frame to frame. I'm just going to click merge using all of the default parameters and let it do its thing. But you can see as it chunks through this, how much more consistent it's going to be. And basically what's happening, as you can see here, as it starts to calculate this, it's getting rid of all of that randomness. It's basically working very similar to a denoising algorithm where, the image information is constant, the noise is always going to be random, so it's getting rid of the random stuff and leaving the most common values compared across the frame window. In this case is set to 5 frames. So it's looking 5 frames before and 5 frames after each current frame, comparing all of that data using optical flow analysis, and deleting the random stuff and keeping all of the good stuff. Again, you're not locked to this. You can always go back and edit it after the fact if you need to, but it's certainly giving you a much more consistent result frame to frame. And again, we're speeding this up for the sake of time, just so we can get on to the next step. And it's done. So now when I scroll through, we can see the result after we've done the z-depth merge compared to the process before. Here we can see all of that chatter, all that inconsistency, and then here we've got a lot more consistency frame to frame. So now when we take a look at this in our perspective view, we can see what we've got. And things there for the most part are looking good, but what I want to do is just kind of scroll through and see if there's anything that kind of pops up that is throwing up some red flags, like perhaps some really out of range information, but everything there looks pretty good. So again, the great thing about having a node-based system is that we can experiment with different techniques to ultimately achieve the best quality results. So what I'm going to do is take a step back, and I'm going to add in a new z-depth solver node. So we'll just select that, and we're going to connect this to the output from our orient scene node. So we've got all of our tracked information, and in this case, instead of going from the current frame only and then tracking that in, what I'm going to do is establish a depth map for the entire clip. So it's going to resolve its depth map on every individual frame. And this is going to take a while, so again, I'm going to speed this up for the sake of time, and we will pick it up once it's done. Okay, and we're done, and that took a total of about 5 minutes in real time. But you can sort of see here how much more detail we've got. I mean, right down to, kind of individual blades of grass and stuff. But again, we've still got a lot of that inconsistency, and we can take a look at this in perspective as well. So we're still going to want to go through and do a z-depth merge node pass. So we'll go ahead and do that and then compare our results. Okay, so now we've got our merged version of that. And, the things that, I want to point out is just, the immense amount of detail that's been solved into this. If we take a look at this again in perspective, you can see like these twigs are being pulled way forward. Same thing with over here on the right-hand side. So it's solving an immense amount of detail. And when you consider how complicated a shot this would be to try and solve and convert using, kind of traditional rotoscoping techniques, it really takes no time at all in PFDepth to create this kind of detail. So comparing what we have here on this current frame to what we solved using the previous technique, there's a significant difference in the amount of detail that we've managed to resolve by calculating a depth map for every single frame as opposed to calculating it for a single frame and tracking it in. So basically what the difference becomes is what is the eye actually able to resolve, and what is your budget? If you've got the time, you might as well go the route of of accuracy and a lot more detail to ultimately get a much better quality result. So what we're going to do is we're going to pass this version of it, because it's more detailed, we're going to pass it down now into a Z-depth render node, or a stereo render node rather, and this is what takes our work and converts it into an anaglyph. Right now we're looking at the anaglyph, but we can take a look at the left eye, we can take a look at the right eye. We can take a look at the anaglyph if we were using NVIDIA's 3D vision technology and I had a supported secondary monitor. We could also look at this export using active shutter glasses. But this is basically all of the parameters that we use to control our conversion. So everything up until this point has all been just about creating our depth information. The stereo render node alone is what actually does the stereoscopic conversion. It reads in all of that depth information that we solved and renders a second eye output. So if we take a look at this in perspective, we can see now that we actually have two cameras separated as part of the stereo rig. So we've got our interocular separation, near plane and the far plane have been passed down for us, and then we also have our convergence. Now the convergence has been set automatically, but I can type in any value here I want. Like if I wanted the convergence to be 10 feet, I could do that. What I like to do is I like to hold down my command key and just drag until I've got the convergence placed exactly where I want it to be. So here I've got it placed at virtually, say 7 feet away from the camera. So that's where we're converging now. Now there's a couple of other things that I can turn on here. I can turn on my disparity histogram, and this is going to basically show me the density of disparity. So the 0 point is what's considered to be my screen, and everything above that is being pushed back and everything below it is being pulled forward. And I can make changes to this. So if I wanted to increase the stereoscopic effect, I can increase the disparity scale. So if I bring that to a value of 2, you can see that it appears that we have more depth to this scene. We can really overemphasize this and bring it up to a value of 5 just to take a look at it. Now we're way overcooking this, of course, but based on how we've got everything set here, we can see how things are being pulled forward and pushed back. Now the comfort area might be around a value of 2, but there's a way that we can see that as well. Based on what our current viewing conditions are right now, I've kind of set it for my current viewing environment. I'm around 3 feet away from the screen, and my screen is approximately 1.5 feet wide. I can increase this. So let's say my screen is more like 2.5 feet wide, and I'm about let's say 4 feet away from the screen. And then I can turn on my comfort zone violations. And this is basically a red light, green light, yellow light warning system. And right now, pretty much everything is green, so it's telling me that I'm safe. I'm not going to be diverging. I'm well within safe value. But if I way overcook this, like let's maybe bring this up to a value of 10, you can see how it's giving me a big warning saying basically the only area here that's going to be safe to view is the center point. Anything above or below is going to be causing my eyes to diverge. And again, if we turn this off, we can see how the image looks, and we can tell it's way overcooked. So again, bringing this down to a value of about a scale value of about 2, we know that we're nice and safe. And by the way, disparity scale and disparity offset, right now the C is activated for both of those, and that means those values are constant. If I turn that off, we can animate those values based on keyframes, and the keyframes will be available to us on the curve editor, so we could smooth in and out of different disparity values. Same thing goes with convergence. Now what's kind of interesting about convergence is if the camera was sort of moving in, like let's say for example on the first frame we're saying that we're about 7 feet. What I can do is turn off constant and turn on fixed, and now what that means is the convergence is now fixed. So as the camera kind of moves through the sequence, you can see that the convergence is now dynamically updating based on the focal plane of the camera at that point in time. So right now we're actually converging 5.2 feet away from the camera, versus at the beginning we were converging basically 7 feet away from the camera. So all of this stuff can be animated, it can be constant, it can be dynamic, whatever you like. The in-painting is what controls how PF depth does automatic inpainting. We can set a look ahead value, so if we wanted to do optical flow analysis for temporal inpainting, that's how that would be controlled. For the sake of performance, if I wanted to inpaint, let's say, across 6 frames, what I could do is do a look ahead of a value of 3 and then use my step of 2. 2 times 3 is 6. So what it's doing is it's still giving me that range of analysis, but with only half the data to compare. So it's going to add in some optimization there. But I'm not going to use any of that, so we'll turn those off. What the edge dilation is, I mean, everything here looks nice and crisp, so I don't really need to worry about any of that. It looks like we don't have to do any inpainting compensation whatsoever. But what I can do is, using the Option F key, bring this up full screen, and we'll play it back and have a look at how things look. So again, looking at this, I mean, we see definite dimensionality to things like these leaves over here, the occlusion of the top of these rock formations versus the background, how these branches down here at the bottom are protruding forward out of the screen. So again, I did all of this with a little bit of hand-holding, but literally not a single rotoshape. And this is what is really cool about PF depth, is that you can get super accurate results really fast without any of that labor-intensive work that you might have to do if you're using other techniques. So there you go, semi-automatic stereoscopic conversion in PF depth. And we're going to make this this project available to you along with the source footage. So, you know, again, by now you've probably followed along, but if you want to take a look at what I did to achieve these results, you can also open up the project file that I'm provided for you. So thanks a lot for watching, and we'll see you in the next video.